We have an update on Elastic Grid Service related to the Telco Cloud Continuum project that we've been working on with Telenor. The theme is all around generating new ROI from AI infrastructure. The project has been a collaboration across Telenor. Sort of the genesis of the idea came from Telenor's Advanced Research Lab, and in collaboration with NVIDIA and Supermicro, the infrastructure has been stood up and running in Telenor's lab, running Avesha software as well for the Elastic Grid Service. The general premise of this is to provide an AI-ready platform that works across this distributed infrastructure and provides that ROI from the compute. The general premise is that as I incorporate more and more compute into the various tiers within my telco cloud, whether that be far edge, near edge, or the core, I need a way to manage those infrastructure assets and to get the best use out of all of them. If I have workloads that are very heavy at the near edge and I have idle capacity at the far edge or the core or my factory, having an ability to move workloads between tiers while maintaining SLA is a critical capability in order to maximize the value that you can extract out of a network. So we're going to go through a demonstration of the Elastic Grid Service platform running in this environment, and we'll take it from there. This feature lets you look at your AI infrastructure spread across multiple tiers within a telco cloud hierarchy. Our familiar levels of tiering within a telco cloud would be customer edge, far edge, think about cell phone tower, near edge, which might be a regional aggregation location, telco core cloud, which might be your national data centers, and AI factory or hyperscaler tier. We're showing two of these tiers currently populated with clusters that contain GPUs. And the representations below here are our list of workspaces and workloads running within each of those workspaces. So as a quick refresher, Elastic Grid Service allows you to utilize GPUs spanning multiple clusters. If we look at our cluster map, you can see this setup is set up with two different clusters, one located at the far edge, one located at the near edge. Each of those clusters has GPU inventory. In this case, we have Grace hoppers that are divided into 7 12 gig GPU MIGs. Same thing for our near edge cluster, also has 7 12 gig MIGs. And our far edge right now is completely allocated. Our near edge only has one of the MIGs allocated, so there it still has capacity. Now, returning to our dashboard, what we see is that one of these workspaces, in particular, an application called Video, which does video analytics, is deployed into this workspace that's spanned across clusters, but there's one pod that's currently queued. And the reason is that it's queued is because there are no available GPUs at the far edge. So that job, since it's gotten introduced to the system, is queued. There's only 7 GPUs. You can count, we've got 7 green dots here. Here's another job that's queued, but it's a low priority job, so that's not going to get time. But this video slice, if we look at that one, this is the video application. It's currently not able to operate because that one pod that's running is the what we call the inferencing pod that would be updating these thumbnails with new inferencing that it's getting from the video streams coming in. So this timestamp 1750 is stuck. We're not advancing any new timestamps. There's no new inferencing happening. And that's because this pod here that's running the Triton inferencing service is queued. It's stuck. Now, the reason that it's stuck is because in our configuration of the video slice, we have a workload placement template, and that's currently in a failed state because it hasn't been able to deploy that workload. And that's because we haven't enabled Elastic Grid Service yet. Now, normally in production, you would have this enabled, and that workload would have already been placed. But for this demo, we're going to turn Elastic Grid Service on, which immediately you see now both clusters come into play, and that workload will be getting distributed from the far edge to the near edge. And you can see that happening in real time. If we go back to the Continuum map, you'll see that that yellow dot already moved over to the near edge because it's now queued against the near edge resources, which does have resources available. Go back to my Continuum map. We were only using 1 out of the 7 GPUs at this tier, and now it's getting an additional GPU for this inferencing server. And that always takes a minute for an inferencing server to boot up. So while that's loading, we do like to see that the AI workload is being run on both the far edge, which here we see the core, and then we see the near edge with the video. So that's now coming up, in the process of coming up. So we should see that go green, which it has. So now we've got 2 GPUs being used at the near edge, and our application logic should be restored, and that now we're advancing thumbnails again. So 1815, if I continue, I'm continuing to get additional new results coming here, 181521, 181529. So there's now live inferencing happening again. This application, even though it's running in 2 completely different clusters on different GPUs, these workloads are able to talk to each other as if they were in the same namespace within a single cluster, but we've spread that namespace across 2 clusters, which we term that a workspace. So the application integrity remained intact, and we didn't have to fail the application. We were able to spread that workload into the near edge, still with very good latency. So we didn't have to go back to Internet Core. We were still able to serve nearby at the near edge, but still part of this application. So we've got AI inferencing being spread both across far edge and near edge. Thanks.